All right. So this is cis256. Today we're going to talk about chapter 7, which is all about recursion. All right. So you can see in this picture, there's a picture of a picture inside a picture. So this is like kind of a visual representation of some kind of recursive phenomenon here. So what is the definition of recursion? In here, computer science and other, domain recursion is defined as the process of defining a problem or the solution to a problem in terms of a simpler version of the solution itself. Okay, so what in other words, a recursion. Give you example. Okay, so if you want to find a way home, all right. So the recursive way of define it of the solution is if you are at home, then you're done. You finish. You find your home. Otherwise, you can take a step towards home. Okay, one step towards home, and try to find that solution again. As you can see in this kind of settings, so this recursion often evolved in basically finding a smaller version of the same similar problem and try to develop the step towards finding the final solution, right? Just instead of like some kind of repetitive work, but also you have each step have one more, so get you one step closer to the solution. Here, example, if you want to count down from the number n to 1, n greater or equal to 1, right? So in this function, you want print the current number, for example, n equal 100 or 10. So you print 10 and it comes to all the way to 1, 10, 9, 8, 7. But so in the recursive way, of course, you can use a iterative way, which is just like a for loop, right? From n to 1 and print n. But in the recursive way, you're solving the problem, which we call countdown, with smaller size. So n minus 1 is one size smaller until n is equal to 1, and you're done. Okay, so that's the way recursive function is all about. Okay, so in terms of the formal recursive function, okay, there is another example here. Let's say you want to add the numbers in the list, right? Which it's a very simple example. In Python, you even have a function called sum to do with one step. But let's think about it another way. Okay, so what if you want to break this list of number into a smaller size? Okay, so you take the first number out of the list, which is a 2, and you add the 2 to the sum of the rest of the items in the list, so which is 5, 10 in this case. And for the smaller problem, you can even further decompose it into the first element in the subset. 5, 10 is 5 and plus the sum of 10. And sum of 10 is simply 10 plus sum of empty set, which is 0. And then you add them together. So finally, you can get this. Formally, you can write this in this function, which you take argument list. If the list is 0, that means empty list, you can return 0 because we know the sum of empty list is 0. That's what we call a base case, right? Other than a base case, you can just call that function again with a subset, except the first element that you want to add. So by doing this way, you calculate the sum of all items in the list. Okay, so now as you can see with these two examples, you probably have already developed some intuition about what a recursive problem looks like. Okay, recursive problem is a very powerful tool, and it's a foundation for many of the algorithms, or in the future in this book and the future courses. So this is very important. 3 laws of recursion. First of all, a recursive algorithm must have a base case. AKA, you need to know when you want to stop. Otherwise, it will be infinite recursion. That will, like this picture shows, it may have some problems. Because eventually, as you know, recursive function uses stack to store function parameters and stuff. And if you have infinite recursion, your stack have a limited size, so eventually you will have stack overflow, where the memory is not enough to hold all the stack variables, and then the computer will crash, right? So recursive function must have a base case to stop it. A recursive algorithm must have moved toward the base case. If your next step is not smaller than the current size, you're not actually making any progress. And then it will cause self recursively, of course. So sometimes you have more than one recursive functions. That's another format. So let's visualize this sum function step by step. Okay, let's do a slideshow. So first of all, you have sum is the first element 1 plus the rest of the sum, which is further composed of 3 plus the rest of sum, and 5 plus the rest of sum, 7 plus empty. And then you return 0, return 7, return 12, that's 5 plus 7, and then 1 plus 15, and the answer is 16. All right, so hopefully you understand this by now. Okay, so here's another example. Previously in the stack, we talked about how to convert a decimal number to a string representation of any base or binary, as an example, right? Now let's see if we can use a recursion. So what's the problem, right? The problem is you give a number of any digits, and the number of digits you want to convert to any base. All right, so as you know, the basic operation for the conversion involve the number integer divided by let's say base 10, right? 716. I'm sorry, 769. And if you want to decompose this one by one, I can divide this number into a 76 and the remainder 9, right? 9 is the one. And then you can just convert 76 to the string representation. So you want to convert integer to string. This is another way. You divide integer by 10. Now you get 76. And modular 10, you get 9. 9 is stuffed into the string. And 76, you do it again. You repeat 76 divided by 10 is 7, remainder 6. So the 6 is being converted to a string and appended to 9 and 7. So the answer is 769. So the smaller problem is basically whenever you divide by 10 or right shift to one digit, you are given a smaller problem until it becomes 0, right? Because eventually you divide by 10 or divide by the base many times until you get the number 0. All right. So for the base that's greater than 10, you can add ABCDEF like for base 16. Okay. Okay. So here's the code. You get a basic digits in string format, right? If the number, so the base case in this case is n is less than the base. Base 2 is 0, 0, or 1. Base 10 is 0 to 9. Base 16 is 0 to f. If the number is not 2 digits, right? It's smaller than base, that's 1 digit. Then you can just return that digits. Okay? Because n is single digits, right? So the digits is represented as a string. So if it's 0, that's given 0, 1. So its position corresponds to the digits, right? So that's what this means. Now, if it's more than 1 digits, well, you can divide it by the base to get it down to smaller digits, and you have the base. So this two-string function simply, are dealing with smaller problem. On the other hand, you already append the and modular base, which is the guarantee to be a reminder is just a less than base. So it will be one of these symbols. So by just divide and modular, repeatedly, you eventually convert the number to any base. Okay. So here is the recursion part one, and hope you enjoy. Bye.